Hello, welcome to the next section, Clustering Fundamentals. In this section we're first going to introduce the basic concepts of clustering and the structure of k-means. Then in the next video we'll look at the two other methods of clustering, db-scan and spectral clustering. Finally we'll learn the evaluation methods. Let's move on to the first video, k-means clustering. In this video we'll first learn the basics of clustering and learn about k-means. Let's get the basics right first. Consider this dataset of points. We assume that it's possible to find a criterion, not unique, so that each sample can be associated with a specific group as shown. Conventionally, each group is called a cluster, and the process of finding the function g is called clustering. Different clustering algorithms are based on alternative strategies to solve this problem, and can yield very different results. This is an example of clustering based on 4 sets of bidimensional samples. The decision to assign a point to a cluster depends only on its features, and sometimes on the position of a set of other points, neighborhood. Let's get started with k-means clustering. The k-means algorithm is based on the strong initial condition to decide the number of clusters through the assignment of k initial centroids or means. Then the distance between each sample and each centroid is computed, and the sample is assigned to the cluster where the distance is minimum. This approach is often called minimizing the inertia of the clusters, which is defined as the algorithm stops when the desired tolerance is reached, or in other words, when the centroids become stable and therefore the inertia is minimized. The mathematical explanation is quite difficult. However, this method is the default choice for Scikit-learn, and it's normally the best choice for any clustering problem solvable with this algorithm. Now take a look at the simple code where we create a dummy dataset. This line is used to create the dataset, and the subsequent one is used to plot and show it. Running it, we get the plot. Here we've got 3 clusters with bidimensional features and a partial overlap due to the standard deviation of each blob. In our example, we haven't used the y variable because we want to generate only a set of locally coherent points to try our algorithms. In this case, the problem is quite simple to solve. So we expect k-means to separate the 3 groups with minimum error in the region of x bounded between -5, 0. So we add this code to perform k-means clustering. Running it gives a result. Next we find the cluster centers and then show the clustered dataset. Running it replots the data using 3 different markers, red, green and blue. It's possible to verify how k-means successfully separated the data. In this case, the separation was very easy, because k-means is based on the Euclidean distance, which is radial, and therefore the clusters are expected to be convex. When this doesn't happen, the problem cannot be solved using this algorithm. Let's consider the case of concentric circles. Scikit-learn provides a built-in function to generate such datasets. This is the code. So we've made use of makeCircleDataset. Running it gives this plot. Here we have 2 concentric circles. I would like to have an internal cluster, corresponding to the samples depicted with triangular markers, and an external one, depicted by dots. However, such sets are not convex, and it's impossible for k-means to separate them correctly. The means would be the same. So I try to apply the algorithm to 2 clusters using this code. The first 2 lines are used to create k-means dataset. Running it, we get the plot. As expected, k-means converged on the 2 centroids in the middle of the 2 half circles, and the resulting clustering is quite different from what we expected. Moreover, if the samples must be considered different according to the distance from the common center, this result will lead to completely wrong predictions. It's obvious that another method must be employed, which we'll look at in the next video, db-scan and spectral clustering.